Megan is going to speak to us about forest resilience, upscaling from the tree to the Landsat level using UAS and the NEON Observatory. So please take it away, Megan.
Great, thank you. If you could go to the first slide, please. So over the past 30 years, forests of the Western United States have experienced a variety of natural disturbances, including wildfire, insect outbreaks, drought, human land use, and also blowdown events. Next slide. And the many data products that exist that represent these disturbances indicate that they're not uniform in their distribution or their intensity across the region. And so this patchwork of potential interactions opens up many regional scale questions related to how multiple disturbances affect tree mortality and regeneration. Next slide. We can think about this in the context of ecosystem stability. So you can imagine two scenarios here in which multiple disturbances affect these two ecosystems. Next slide. And depending on the magnitude of the effect in this very simplified schematic, that results in ecosystem resilience, whereby the system is perturbed, but it returns to its pre-disturbance state, or an ecosystem transition, meaning a shift to a new state. Next slide. And many studies examining these questions are conducted at relatively small spatial extents, often at the stand scale. We're uniquely positioned in this time of increased data availability and processing power to look at these questions across regions. So this is a chronosequence of fire, beetle kill, and drought paired with a satellite drive metric of forest state across the Southern Rockies to evaluate forest recovery following fire. So this graph is showing you forest state on the y-axis over time since disturbance on the x-axis. We can see a pre-disturbance state indicated by that dotted horizontal line, mortality immediately following fire at time 0, a period of lagged mortality, and then finally recovery. So I find that if there's beetle kill prior to fire, which is the bright red line there, not only does that period of lagged mortality last longer, but forest recovery is delayed by about 7 years relative to a fire-only scenario, which is the green line on that graph. And drought, which is the dark red line, further delays recovery time. Next slide. So those previous results use a data set that's relatively spatially coarse, and it's available for a limited temporal window. So in order to capture subpixel change across decades, we're using data from drone-mounted multispectral sensors and plane-mounted hyperspectral sensors from the National Ecological Observatory Network, or NEON. And that helps us to bridge that gap between ground-based field inventories and moderate resolution satellite data. Next slide. The idea here is to extract the spectral signatures, or the unique way that light reflects off of an individual tree, from the drone and from the NEON data at the location of each stem based on the ground-based data. On the bottom left or the bottom right there, those are NEON hyperspectral data, and each line is an individual stem across the wavelengths that NEON covers. Next slide. These spectral signatures are then aggregated to the plant functional type level, for example, deciduous forest or coniferous forest. Next slide. These are the samples in spectral space to show you that they are differentiable by plant functional type. And these clusters are then used as end members for spectral and mixing analysis of the Landsat data. Next slide. If unmixing isn't familiar to you, just know that the end result is a data layer for each year that designates the proportion of each 30-meter Landsat pixel that's occupied by each plant functional type over the Landsat historical archive. Next slide. I want to show you an example of what one raster of this product looks like. Each pixel in this Landsat data here is designated as the proportional occupancy of a given plant functional type. And you'd have a raster layer for each plant functional type for each year. Next slide. This response variable, the unmixed Landsat data that I just showed you, is paired with data on disturbance history under a Bayesian modeling framework. These are simulated results. Similar to the last graph that I showed you, the X here is time since disturbance, and the Y for simplicity is one state variable, percent forest, for example. But in reality, this is modeled in n-dimensional space, n being the number of plant functional types that you're interested in, that you're tracking. So we have a pixel that's occupied by some percent forest, which we can see in that dark blue section on the far left. And in this simulation, fire occurs, and there's some post-fire mortality, which is the bright orange part of that graph. Fire is followed by non-drought in condition 1, and it recovers. and fire is followed by drought in condition 2, and it doesn't recover. So in condition 2, a state change is indicated because the recovery trajectory doesn't return to within the historical range of variation for that state variable. Next slide. So in summary, this framework allows us to make extrapolations about the effects of disturbance history on forest resilience at the landscape scale. And drones are a critical piece of that framework. They, along with the NEON data, allow us to upscale from the tree to the Landsat level. So this is one example of how we might integrate drone data with satellite data in order to answer fundamental ecological questions. And then last slide. So thank you.